Good morning, everyone. It is a great pleasure to welcome you all to the Global Water Futures Core Modeling webinar series. I am Pravin Rokaya. I'm the coordinator of the Core Modeling and Forecasting team. I, along with Core Modeling leads Al Petronero and Martin Clark, want to thank you all for joining us today. I know we all have too many meetings, online meetings and webinars these days, so we really appreciate your engagement. Today we have Dr. Trisha Statnik from the University of Calgary, who would be presenting on the advances in water resource management. It would be about 45 minutes of presentation, followed by 15 minutes of question and answer session. Before we begin, I wanted to share that next month on 7th of January, we'll be having Professor Martin Clark from the University of Saskatchewan, who will be presenting on advances in geospatial intelligence. So please stay tuned. Today, I'm very pleased to introduce Dr. Trisha Statnik from the University of Calgary. Trisha is the theme leader of the water resource management theme of the core modeling program. This theme focuses on two main areas. First is the application of existing water management models, and the second is the integration of water management in land models. Trisha, we are very happy and grateful to have you here today. The floor is yours.
Thank you very much for the introduction. I'm going to share my screen and you're going to tell me if it is working okay.
Yeah.
Okay. Are we good? We can see the slide?
Yes.
Okay. Excellent. And in keeping with today's theme, behind me in the background is actually a picture of the Squatum Generating Station in northern Manitoba. So thank you everybody for joining. Good morning or good afternoon, depending on what part of the world you're connecting to us from. It's my pleasure to update you on behalf of my team, the Water Resources Management Modeling Core Modeling team, on the progress that Global Water Futures is making in the area of water resources management. As Praveen said, my name is Dr. Trisha Statnik. I'm a Canada Research Chair in Hydrologic Modeling from the University of Calgary, and I've been with Global Water Futures Network since the beginning. Okay, let's see here. Good. Okay, so I wanted to begin with the fundamentals, which is to throw up very quickly the Global Water Futures Mission Statement. Right in the definition from day one of this CFREF was bullet number 2, to predict water futures. So modeling has always been a fundamental component, front and center, for the capability of Global Water Futures to meet their mission statement. In order to be able to do that, we need a lot of information, a lot of data, but we also need to really invest in developing better models. Specifically for this presentation, we're going to talk about how to assess change in the context of human or natural land and water systems, specifically the human influence and how that's changing the water systems. Without this information, we can't expect to have accurate predictions that help us to get a better handle on future water supply. So hopefully most people that are tuning into this webinar are very familiar with this. I like to call it Hydrology 101, and I'm going to give you a really brief synopsis here. But when we first learn about the water cycle, this is kind of the conceptual idea that we learn about. We learn about the ideal relationship where we have some sort of pooled or ponded water on the land surface. That water is subject with heat and energy to evaporation or evapotranspiration from the land surface, as well as uptake by plants. That in turn forms clouds, which then becomes rain or snow somewhere else. This can of course be complicated by some factors, including climate change, but fundamentally the relationships and the connectivity here between the atmosphere and the land surface stays the same. That is not true when there's human interference on the landscape. So instead, this is what happens. We end up with a much more complex relationship for the water cycle, specifically different connectivity between the surface processes. Human interference has been playing an increasing role in modifying the discharge in rivers, or the amount of water that ends up in aquifers and stays in aquifers, and the amount of water that's discharged to our ocean systems. It doesn't affect the total volume as much as it affects the timing of that volume and when it's reaching the endpoints that it reached before. And this of course has long-term implications for climate change, because climate change acts on a process level. So if there isn't as much surface water, or if there's more surface water, that in turn will change the evapotranspiration, which will change the connectivity with the climate cycle. Reservoirs specifically, we're going to talk about lakes and reservoirs, disrupt the natural rainfall runoff relationship. So they actually attenuate the water. It doesn't get released on the same time cycle, and therefore we don't have the natural rainfall runoff relationship, but instead we end up with something that's more fragmented. An example of this I'm going to talk about later on in more detail would be hydropower production in cold climates like Manitoba or Quebec, where the peak hydropower production actually occurs in winter, when typically the water supply is at its minimum. So instead we store the water and use it at a different time of year. So this is just a summary from the literature from Grill et al. Of a fragmentation index that was introduced. And they've actually done this work globally. What I'm showing here is just for North America and South America. But it's basically designed to describe the amount of fragmentation or disconnection between river systems, as well as the degree of regulation. So those two don't necessarily mean the same thing. You can have a highly regulated river that isn't fragmented, and similarly, you can have a fragmented system that isn't as well regulated. You can see that in North America, fragmentation is quite significant, with not only a high degree of storage and diversion, but significant impacts to the regulation of discharge, which affects the seasonality, particularly in central Canada and across some of the Canadian prairies. This has also been changing through time, and the amount of regulation has actually been increasing over time. So to show you that, or to demonstrate that, this is a study that was performed by Dr. Stefan Deary from UNBC and myself in 2018, where we actually looked at paired river systems that were either regulated or unregulated within the same general watershed, geographical extent, and physiographic regions. The graph on the right shows that when we normalize mean daily discharge and plot that by considering the actual day of the week for different periods of time, one which is an earlier period, 1961 to 1988, and one which is more contemporary, 1989 to 2016. And we see distinct differences or separation between the regulated and unregulated systems. Specifically, and quite obviously, the red and the green are for the unregulated river systems. And you see much more pronounced changes in the average annual hydrograph, where you can actually see a little bit more seasonality, and a little bit of difference between the earlier period and the more contemporary period. But as you move into the regulated system, which happens to be the blue and the black, not only do we get a much different looking average annual hydrograph with that weekly cyclicity happening, where the day of the week actually makes a difference in terms of the amount of discharge, but we also see a much bigger separation between the blue and the black line, which is the earlier period, the black line, and the more recent period, which is the blue line. So over time, what we're getting is this flattening of the average annual hydrograph, where there's less seasonality and a much more uniform distribution of discharge throughout the year. So in order to be able to consider these effects, we have to now consider that when we set up hydrologic models, a significant amount of human interference is occurring on the landscape. This is for the Hudson Bay watershed system, which represents about 1/3 of the Canadian continental interior. And this is some work from Andrew Tefts, one of the people in my group, that shows the different kinds of development that is occurring within the basin that we've worked to embed within the model. Within this particular basin, more than 70% of the discharge entering Hudson Bay is actually regulated, and more than 40%, 47% is actually considered to be intensely regulated. It's important, therefore, that our hydrologic models account for these kinds of changes that alter the natural course of discharge across the landscape. We're extending our analyses to the North American continental scale as well as to the Pan-Arctic scale. So if we take a look at, There we go. If we take a look at what's happening across the Pan-Arctic scale, this is work that's really just beginning within my group. The last two columns in this block diagram here represent a comparison of all regulated rivers grouped together and all non-regulated rivers. The different colors represent the decadal trend over time. And you can see that not only do we have differences in the magnitude of the trend, but probably what's even more significant, the stars represent statistical significance of the trends. You can actually see that the significance in terms of how we detect those trends is changing. And of course, this is for Hudson Bay or North America, but we also see similar effects happening in Siberian rivers or in Eurasia. The Ob is extremely regulated. It's got some fairly large upstream reservoirs. And if you compare that to some of the unregulated rivers, such as the Kolyma, for instance, you can see that not only does the magnitude of the trend change, but also the significance. So this is important because without regulation in our models, predicting changes into the future means that we could actually be wrong, not only in terms of the trend that we detect, but also the significance of that trend. And that's really what this figure here shows from some of our earlier work. It's a lot to take in, but I'll just say that the bottom of the column represents the earlier period, so from 1981 up to 2070 as you move to the top. And then these represent the months of the year. This is for regulated river system, the regulation embedded in the Legrand River versus the model run when we've stripped all the regulation out. And then the last figure here represents the difference between these two. So when we compare these two with climate change scenarios, so these are driven by GCMs, an ensemble of GCMs, we really see an intensification of the peak discharge over time. So if you go up the column here, then you can see that the peak discharge, you're getting more orange and more reds. And if you compare the regulated to the non-regulated, we can see differences in terms of when that peak discharge is actually occurring, similar to the results that I showed previously. You can really see that when we look at the difference, but what also stands out here are the changes in what we call the shoulder seasons. So it's not just the peak discharge that's changing, but it's really that lowering of the peak discharge and increasing of the shoulder seasons to lead to that flattening trend. Okay, so the big picture goal, where does this leave us? Namely, if we wish to meet the Global Water Futures goal of improving future water predictions, we must account for landscape scale changes, including those imposed by human alteration of the flow regime. So that's what we're talking about today, and that's really what the Water Resources Management Modeling team has been charged with. Our goal is to develop approaches that facilitate meeting that agenda across a diversity of models and landscapes and spatial scales. There's really two ways in which we approach this problem. Number one is using integrated water resource management models, which I'll talk about. And that really allows us to assess the impact of the decisions that we make on the landscape. And then the second one is to embed reservoirs and water management into hydrologic models. The first approach, the integrated water resource management models, has a more detailed representation of water management, but the second one has a more detailed representation of hydrologic processes. So neither one is better than the other. They both have different purposes, and that's why our team is pursuing both. In terms of, the scope of the water resource management modeling team, we're talking about pan-Canadian scale, so across Canada, but even more so than that, most people on our team are aiming for global scale. So really looking at large scales to apply these models to and these modeling approaches. A key task is to make this model agnostic, so not specific to any one model, but approaches that can be uptaken by a variety of different models. And the idea is to represent human influence on the water cycle. So we're talking about lakes, wetlands, as well as managed reservoirs, diversions, dams, and irrigation, as well as infrastructure, the infrastructure itself, as well as the operations and the decision-making behind that infrastructure. So our team has broken all of this task or all of this agenda item, all of these agenda items down into different work packages or tasks. And that's how I've structured the presentation. So I'll briefly walk you through the different areas of research that we have going on, starting with network-based routing and adding lakes, wetlands, and water management to standalone routing products. Then I'll summarize some of the work we're doing to embed managed regulation rules into hydrologic models. And I'll end off by talking about the work that we're doing with the integrated water resource management models. Before I launch into the details of some of the work that we're doing, I wanted to outline the rationale that is guiding some of the choices we're making, just because that might help address some of the questions you have as we go. So as I mentioned, first of all, these have to be generalized approaches, not specific to any one model. They have to be computationally efficient because the goal is to apply them across large scales. We take a standard practice towards coding. And so we're always trying to communicate about how we're coding and make that code publicly available and readable, hopefully. So everything is being developed with the intent of making it open source. We're documenting everything. Usually that gets produced and published on a GitHub. Everything needs to be reproducible, including our results and our data. And with that, we're also doing benchmarking of the models. So I might have missed a few in there, but these are the core principles that we try to abide by. So I'm going to begin with the first approach, which is the work that we're, so Dr. Shervan Gahari from the University of Saskatchewan is doing to look at network-based routing products. The work is being done initially, at least, through the MISRoute model, which is a vector-based routing model. And the work is being done to incorporate lakes and reservoirs within that model. So network routing tools are of interest to us on the core modeling water resource management team because they're highly efficient. They can be used across a variety of models. Of course, all you need is runoff, but that runoff can come from a variety of sources and not just any one model. It produces spatially distributed streamflow or discharge, and it produces that across really large spatial scales. So they're very handy tools for looking at future analyses. The goal here is to improve specifically vector-based river routing functionality in MISRoute, looking at embedding lakes and wetlands, as well as managed features such as reservoirs, irrigation withdrawals, diversions, and any water allocations. So the approach itself that Shervan is taking uses minimal inputs. That's in the banner across the top here. Oops, my bad. Across the top here. So first of all, the hydrological input files. What's required is some sort of runoff from a host model, and that could be anywhere from a global climate model to an actual land surface model or hydrologic model, as well as some idea of open water evaporation and precipitation onto the lake surfaces. In addition to that, some water management information is required, target lake volumes, if there is such a thing where there's an ideal water surface level that lake is managed to be at, and any water that's taken from the river segment. New inputs and water management states and fluxes are then distributed across multiple CPUs to enable parallelized computing. So that's one of the advantages of this type of routing and why it can be so efficient is it's actually parallelized. A lake module that's embedded within the routing network will then determine if the lake is actually on the river network or if it's large enough to be considered a lake on the river network or whether it's just part of the river. And so this often happens in areas where the river just gets slightly wider, but perhaps that's not actually a lake and doesn't behave quite the same as a managed lake. So it can be either treated as river network or lakes, and that will depend on size. And so the outflow will be governed from the lakes either by parameters, so that's the parameterized module, or by target volume. And so if there's an ideal volume that lake is managed at, then that can be one way that the outflow from that lake is determined. And lastly, Any abstractions or injections of water fluxes within the lake network, or the river network, sorry, are added to or from the river network to produce the output. And so this is showing some of the results. On your right, you have a simulation for the Mackenzie River Basin and Great Bear Lake within that system. And on the left, you have the lake level fluctuations that are being simulated by Mesoraut with the lakes embedded within the river network relative to the observed daily lake level. The network topology was taken from hydrolakes and HDMA. The host model that produced the runoff was CLM, and this was a parametric storage outflow type relationship that produced this output. And so as you can see, the model's performing quite well. Moving to the prairie environment, this is an example with Lake Diefenbaker outflow from Gardner Dam, as well as monitoring the response at the Saskatchewan River at Saskatoon. You can see here the discharge relative to time from the observed in red here and the modeled in blue. The river network topology here was also hydrolakes and HDMA. The host model in this particular case, there wasn't any observations were from upstream gauges. So that's how we were forcing the modeling in this particular case. And there was 2 gauges that were looked at for that. The lake simulation, instead of being parametric, this time was target volume based on using water surface level from Gardner Dam. And then it was validated at Saskatoon. So also fairly strong performance from the early results here. So future work for Chervan includes the development of a coupler for lakes and reservoirs, which means online coupling of irrigation demand and water management from machine learning techniques, integration of alternative parametric lake schemes, and potential global application of Mesoraut. So that caps off the network routing. Next, we have the embedding of water management rules and regulation into hydrologic models. And there's 2 contributions to this particular work. I'm going to start with Dr. Fouad Yassin's work. He's also from the University of Saskatchewan and the Global Institute for Water Security. So Fouad's work is to develop and test improved reservoir operations models and to couple those models with hydrologic models. In this particular case, the case studies that I'm going to show you are with the mesh hydrologic model. And then the goal is to really focus on a reduced parameterization of any kind of reservoir operations model, such that the application of the model can be used in data sparse or data limited regions. So requiring only inflow, outflow, and lake storage data. The model or modeling approach that Fouad has developed is referred to as the Dynamically Zoned Target Release, or DZTR model. In this particular model setup, there's 5 zones, 1, 2, 3, 4, 5. Each one has flows and discharges. So there's 5 storage zones, and the reservoir release can occur either through the bottom outlet or spillway, or across the spillway. And you can see that up here. So there's really 2 outlets from the reservoir. There's a parametric piecewise linear function that's used to approximate the reservoir release rules. So Fouad has applied this in a study that's already published. You'll see the references on slides here at 37 reservoirs located across the world. And here in this particular results slide, we're showing the Nash-Sutcliffe results on the bottom of the right graph for each of those 37 reservoirs. The red represents no reservoir versus the black and the gray, which have an implementation of the DZTR model. In this particular case, the way the results were presented by Fouad was by benchmarking. So he looked at 2 Nash-Sutcliffe thresholds, 0.25 and 0.5. And then with the DZTR model implemented, he found that 90% and 50% of the models of the sites, the 37 sites, met those thresholds respectively. But when no reservoir was implemented, only 45 and 30% met those 2 particular benchmarking thresholds respectively. Fouad has also introduced an indicator of regulation. It's called C, where less than 0.5 represents low regulation scenarios and greater than 0.5 represents high regulation scenarios. And you can see that on this slide, which is where the DZTR model was implemented within MESH. First task was to actually introduce an irrigation algorithm because the application scenario across the prairies had fairly significant irrigation withdrawals. And then the model was applied along with the irrigation withdrawals. And you can see that for the WAC Bennett Dam, that's considered a fairly high regulation scenario, so C greater than 0.5. And the importance of the model was fairly significant here. So the irrigation algorithm, or sorry, the uncalibrated model though, generally improved with the model being used relative to no reservoir. And you can see that in the scores at the top. If we look at the Waterton reservoir here, in this case, the storage-based simulation showed lower performance for the Nash Sutcliffe, and this is for the St. Mary's River and Waterton dams, and a negative Nash score for the storage for the Old Man and Ghost dams. The simulation was a reasonable representation of the storage variability, but with considerable underestimation. And the underestimation is related to the estimation of inflow by the mesh model. So with more calibration and improvement in the mesh model, it's anticipated that these results would in fact improve. So future work for FUAD is to reduce the parameterizations of this particular model so that we can expand its applicability for data sparse regions, particularly looking at expanding the scope to more global, and looking at alternative sources of data for some of the inputs, including satellite-based observations. And then to regionalize the reservoir operation based on classifying from political, social, and geomorphological and climatological factors. So next, and also within the hydrologic modeling realm, so embedding regulation within hydrologic models, is Andrew Tufts' work out of the University of Calgary Hydrologic Analysis Laboratory. So Andrew has been working on embedding regulated discharge within the HYPE hydrologic model, but with the idea that this would be applicable beyond HYPE. The constraints of his particular project are that the model is efficient for long-term simulation, looking at doing future climate change scenarios, that it has to be continental or global scale simulations of daily operations using minimal inputs, and again, that any input data can be derived from global climate models. So similar to FUAD's work, Andrew's model also separates reservoirs into different zones. The difference is that these are really based on operational zones, and that there's basically monthly or conditional or unrestricted parameterizations that are associated with the different water surface levels. These, depending on where the water surface level is predicted to be, there's going to be a target water surface level that the results are always pulled back to. The model operates only on publicly available inputs, such as daily flows from Water Survey of Canada or the global runoff data set from the GRDC. So you need inflow, outflow, and some idea of mean surface area of the reservoir. So Andrew has done some early validation work of his model using 19 reservoirs between Canada and Russia, so really extending this to the Pan-Arctic domain, looking at varying relative sizes and varying levels of record quality. So that was important for us to include in the analysis as well. So some records are more consistent than others. So there's going to be days where water surface level and storage are both available, and then days where they're not. And we wanted to look at the impact of that on the results. Some preliminary results to show you here. This is a plot of storage on the x-axis versus outflow. The different colors represent with the reservoir regulation routine in, which are the red dots, versus without the reservoir regulation. And generally speaking, only the model with the reservoirs achieved a Nash greater than 0.5 for both storage and outflow, compared to the model without the regulation. And this was achieved both in the reference and validation periods. Record completeness significantly impacted the results here. The best results, so in the top right corner, definitely had more observations, which typically consists of greater than 8 years of water surface level and outflow consecutively. So some future work in this area is to look at parameter uncertainty for parameterizing the model and how that impacts the results. So Andrew is right now running cascading uncertainty analyses where he looks at the impact of the reservoirs in series and parallel. And then the goal will be to extend the application of the model to all of Canada, the Pan-Arctic domain, and then hopefully eventually global. So that brings us to the second type of approach, which is the integrated water resource management model. Mustakim is working on this from the University of Saskatchewan in conjunction or in collaboration with Dr. Saman Rezavi. This is where we overlap with the IMPC project, looking at the modeling within the Saskatchewan River Basin in the integrated water resource modeling framework. So this is an example of the integrated water resource management model that has been set up through IMPC. The difference with core modeling is really that we're not focused on specific stakeholder inputs or outputs, that we're looking at more global and large scale application of this kind of approach and not any one specific problem. So in this particular case, Mustakim has set up the model from the Manitoba-Saskatchewan border up to the headwaters of the Rocky Mountains. And I'll talk about it a little bit later in the next section, but Dr. Masood Asazada and his team from University of Manitoba is focusing on constructing the model from the Manitoba-Saskatchewan border downstream to Hudson Bay. So this is the second model. The core modeling team will see the interface of these two models to produce a Nelson River Basin-wide model. Within this model, we can break up the river network into different key regions or operating groups, and we can add different kinds of interjurisdictional water agreements and test different scenarios. So that's really the main advantage of setting up such an integrated framework in a water resource management model. So the difference between an integrated water resource management model and the hydrologic modeling approach is primarily that decisions are made at significant nodes within the system, represented here by the different junction points, which are the blue dots. You can see the legend on the right-hand side here that shows you the different types of regulation that's embedded within the model as well. And at those different nodes, water balance must be achieved along with other operational constraints. So the model accounts for more than just water balance and actually finds possible and even optimal solutions based on balancing an entire network of decisions. So it's a slightly different setup in terms of how the complex mathematics are solved. Different types of regulation can then be embedded in different types of decision making, and then we can alter either the water management, the water inflows from climate and hydrology, or the actual decisions that are made to test different kinds of outcomes. So unlike embedding regulation into a hydrologic model, the application of an integrated water resource management model affords the opportunity to actually test the impacts of human decisions. It's not a standard code for all regulation, but rather an optimization of the whole system. So that you have the opportunity to see that if you change a decision at any one point within the system, there's going to be a trickle down effect that then alters decisions that might be made at subsequent downstream nodes. This particular model of the Nelson River system happens to be one of the most complex integrated water resource management models developed that we know of at least, but the system does allow us to test different water policy and management decisions across the prairies. And so this is a very badly needed system in this particular part of the world. Therefore, we can perform different stress tests. And so stress tests are basically worst case allocations or worst case scenarios to see what happens within the system and how far we can push the system limits before things literally or figuratively blow up. So one example is a long-term drought. Can we actually meet, is it possible to meet the current water allocations set out by transboundary water agreements such as the PPWB, the Prairie Provinces Water Board, or the International Joint Commission, the agreement between Canada and the US. So future development of this modeling system within the core modeling team is to couple this directly with hydrologic models. So to create dynamic streamflow inputs driven by climate scenarios. And then also to couple with the upstream and the downstream. So the Saskatchewan River model and the Nelson River model from Manitoba. And then to test vulnerability of the system to different stress scenarios, specifically within the Saskatchewan River Basin, but also downstream in the Manitoba system. This will include looking at incorporating climate change as well as new infrastructure developments. So last but certainly not least is building off of the initial integrated water resource management model, but to incorporate cold regions effects, or to really to adapt the integrated water resource management system to account for ice-on effects. And this is work that's being led by Dr. Masoud Assazada out of the University of Manitoba, who is also a researcher within the Global Water Futures Network. So why do we want to look at cold regions specifically within integrated water resource management frameworks? Well, this affects basically the relationship between daily discharge and stage, which would be on the y-axis here, or water surface level. So for open water scenarios, you're going to have a lower stage height for the same relative discharge as you have when those conditions are under ice. So when we have ice on condition, we're going to have a higher stage. This results in uncertainty in our actual ratings, so our rating curves, which lead to our observed discharges, which we calibrate our models to. But it also, more importantly, leads to a change in operations and decision-making within the system. Specifically, most jurisdictions in cold regions and hydropower producers will run what they call ice stabilization programs. This is where at the onset of freeze up, they will enter a period where they purposely lower the discharge to create calm, quiet conditions to prevent the buildup of what we call frazzle ice. This is a picture of what frazzle ice can do. It can entirely clog the intake gates to a hydroelectric station and actually shut it down for several days while those gates are cleaned off. So that's obviously worst case scenario. We don't want that happening. So this changes ice, the presence of ice changes the way in which river networks are managed and certain points within the river network. So this is a schematic of the hydroelectric power generation system within Manitoba. When we embed this in a water resource management model, we're talking about modeling this area highlighted in orange here, which from a network schematic point of view looks like this. And the areas that are circled in red here correspond to areas 4 and 5, which are points at which the Manitoba Hydro operates an ice stabilization program coming into the onset of freeze up. You can see here the effect of the presence of ice conditions. This is a discharge record for the Nelson River West Channel, which is right near GenPeg. It is the forebay to the particular GenPeg generating station. And in each particular year, the rating curves accurately simulate the channel flow with no ice. That's what's shown here in green. But once we have the presence of ice, then you can see that we end up with a disparity between the simulation from the rating curves as well as the measured channel flow from an integrated, so measured compared to the simulated from the integrated water resource management model. So we want to be able to address that particular time of year during freeze up. So an ice factor is computed, which basically records the deviation between the simulated and the observed flow. This is used as a baseline condition, and then a statistical regression model is applied that relies on daily air temperature only, such that it can be run under future climate scenarios. And then that statistical regression model is applied to the actual integrated water resource management model. And you can see the results here. The results indicate a significant improvement when the ice-affected discharge is accounted for, which is the orange line, relative to the blue measured flow, compared to the dashed line, which is just the rating curve without the ice-affected discharge accounted for. And then you can see the statistics down here. So this approach is leading to improved results, both under a calibration period as well as a validation period. So additional work in this area includes testing and verification analyses within other parts of Manitoba Hydro's system and scope of operations, specifically looking at the South Bay Channel or the diversion from the Churchill River. And then to apply this as a more generic approach for all ice-affected control points within the entire Nelson River system, which includes the Saskatchewan River water resource management model. So just to wrap things up here so that we leave some time for questions, accurate prediction of future water supply and security really necessitates modeling, and specifically within that modeling, accounting for the human influences of that water resource discharge. In recent decades, we've seen that fragmentation and regulation of the watersheds is increasing. It's increasing in its intensity as well as its scope of development. And future development is also slated, and there's a suggestion that the intensification of fragmentation is only going to increase. So we're therefore, as a water resource management modeling team, testing and applying two different methods of accounting for these human effects or human influences. The first is integrated water resource management models, and the second is using hydrologic and land surface models with regulation embedded in them. The deliverables that my team is responsible for by the end of 2023 is to look at supplying continental or global scale network routing that includes lakes, wetlands, and regulated reservoirs, irrigation, and diversion withdrawals. The second is some model agnostic codes that allow for minimally parameterized descriptions of regulated releases within hydrologic models that can be embedded in any hydrologic model. And the third is dynamic integrated water resource management scenarios of the Saskatchewan Nelson River Basin that is capable of optimizing a system response within cold regions to look at how discharge scenarios are affected. So for more information or a copy of this presentation, you can visit my group's website. Thank you for your attention, and I'm happy to address any questions that anyone might have.
Thank you, Trace. That was a very informative presentation and really a lot of novel work being done. We'll be now moving towards the question and answer session. So I have a question from Simone Lin, and I think it is specifically related to the DZTR model. So what he's asking is, it looks like the model requests only a sparse amount of data. So can you explain, like, what are the minimum data required for that model?
Sure. So I believe, I should have introduced them, but my whole team is online here. I thought it's best to go right to the experts. So maybe Fuad can answer that question specifically.
Hey, can you hear me?
Yep.
All right. So yeah, I just saw the question, and yeah, the data requirements are outflow and storage, just the minimal requirement without any calibration of the reservoir parameterization. But if you want to parameterize those reservoir parameters, you need inflow as well, inflow, storage, and outflow. And another good question was about the number of outlets. So at the moment, it has only one outlet. The implementation has one outlet, but I can see that there is a possibility to extend the number of outlets, ruled-based outlets, but the only thing I can think of is like there must be some priority. So one of the outlet has to have primary demand than the next one. So that way you can parameterize them outside and supply each parameters. And after releasing the first one and the next level available, will decide output for the second one. And in our current implementation, as a second outlet, we have abstraction. So the rules are not hugely affecting the abstraction because we implemented on Saskatchewan, for example, for Lake Diefenbaker. We have released to the main stream and to main stream of Saskatchewan River Basin. And for the Coppell system and for the Coppell, we just did abstraction. We didn't take it as outlet regulation. So that's another approach to implement it. Yeah, I hope that answers your question.
Well, I think this question also can be related to the reservoir module that Andrew and Servan are also working. Andrew and Servan, do you also want to add if there is multiple outlets in your lake, then how those are represented?
Yes, I can answer that very quickly. We have our current model incorporates an option for a second outlet. And so we've implemented that in Southern Indian Lake, which is the Churchill River diversion, and at Lake St. Joseph, which diverts water from the Albany to the Winnipeg River and ultimately Nelson watershed. And similar to what Fuad was discussing, it's parameterized for both outlets, with the outflow from the main outlet typically being prioritized in a very hand-waving kind of way, but they use a shared volume, of course, so the discharge is keyed to the volume on that time step.
And in terms of Shervan's model, I think the end goal is to embed both models into his, but maybe he can more specifically address that.
Yes, so regarding the first variance, the outflow from the lakes, at this moment we have one, but our future work is on the coupler, so most of the complication in the river network topology will be handled in the coupler. It's not efficient for such a model to be handled inside the model, so it will be handled in the coupler and it will be passed to the model. And at the same time, we also need information for basically constructing those. So we should think about how those few outlets will work, which is another challenge. But the work is on the way, and we are aware of it, and we will address it. But the other thing was about the parameterization, or yeah. So basically, on MISO route, we make it capable for two ends of the spectrum. So one is data driven. If the data comes from artificial neural network, water management models in the online fashion, the future SWOT median for the altimetry of the lakes level, so we can readily take that into the model at this moment. And then we have also parametric. So at this moment, we have only a simple parametric fashion in the model, or parameterization in the model, but we are at this moment doing Hanasaki, which I think has around 20 something parameter. We can do more, we can do less. And we are also working with Andrew, maybe brings some of the parameterization from HYPE. Those are all possible.
Thanks, Andrew and Servan. We have a second question from Sahid Golian, and he's asking if these different reservoir modules that you guys are developing, if they are, in different platforms, written in different languages, or if they can be linked together.
Yeah. So within this water resource management modeling team, all of our model developers have kind of a subgroup meeting to talk about code standardization. Fortran is the primary coding language, believe it or not, and that's simply because the hydrology models that they happen to be working with are generally speaking written in Fortran, but that doesn't include the couplers. I think some of the couplers are written in Python, so there are different languages that are used depending on the necessity of the particular task. but the answer is yes. A lot of attention is being paid to make sure that these particular codes interface and are interchangeable. So I don't know if Shervan wants to add to that, because I know that his goal is to adopt the code from the Fortran, from the hydrologic models, which is being coded in Fortran. So Shervan?
Yes, for the meso route, everything is in Fortran. So also the coupler at this moment is in Fortran. We can do pre-processing, post-processing, and something like Python, but we try to keep everything in Fortran so we have the efficiency. But still, doing things in Fortran does not mean that we cannot, let's say, couple it with other things. So always coupling possible. We just should first ask what type of couple, and then we will think about it. I think it should be straightforward. Yeah.
So maybe Masood and Muscatine can speak to coupling with the integrated water resource management model, because I know that different languages had to be used there for the couplers, at least in the case of the Nelson River model.
Yeah, for our case, water management model in Saskatchewan, Alberta. So we are using a Python platform to customize our water management model, and we have also other modules like irrigation demand model and other issues. So we are using Python to implement those, but I think it's gonna be easy, because in downstream part, Nelson, they need the outflow from our system. So it should be easy, because it provides outputs in MDB file or Excel file, so they can easily couple the downstream part.
Yeah, and talking about coupling ModSim with other platforms, we have tried that, because we can run ModSim standalone and call it from almost any other language. It's an executable file. You can call it from MATLAB and then get the results. As Mustaqim said, you can read that MDB or CSV file and then transfer the result into any other software platform that requires that input-output. Then run that as well, and then return the result into ModSim. For example, we coupled ModSim with hydrologic model to get local inflows to upstream of control points along the Nelson River, and that went successful. So yeah, coupling is not that challenging. Except for the required computational resources.
So we have another question from Haley Carlson, and saying that she understands that core modeling work is model agnostic and does not focus on particular question or situation. But if there is a plan to disseminate some of the information in some of these results to the non-academic partners to contribute in practice.
Yeah, so I would say this is part of it, right? That was the vision of these webinar series, is to kind of get the idea of what we're doing and updates on what we're doing out to the broader community through webinars. In terms of stakeholders, we have a pretty strong link in our core modeling team's case to the IMPC project, which is largely stakeholder driven. So I know that the integrated water resource management models are both being developed in conjunction with hydropower utilities and other flood forecasting stakeholders across the prairies. And then similarly with the hydrologic models, they're very closely tied to different stakeholders. So the answer is yes, we're in constant communication with those stakeholders. Of course, we also plan to disseminate these results through the traditional route, which would be the peer-reviewed literature as well.
We have a question from Al, and he said that he's curious about the work with dairy at the beginning. Are you saying that over time the reservoir regulations are changing? I may have missed that, but it looks like the outflows are flattening.
Yeah, so I guess what I'm saying is there's a stepwise introduction of additional regulation, more so than the regulation is changing over time. So if I flip back to that earlier slide, it'd be easier if I exit, but that will take longer because then I have to reshare. What we're seeing is in terms of separation of the what we call the early period versus the later period is actually, so the black versus the blue is actually caused because of new regulation that was introduced in the 90s and in the early 2000s that's captured in the blue line. So as the river system becomes more regulated, you're going to see an exaggerated effect of that flattening. But the answer is yes, absolutely. We're seeing an intensification of that flattening over time as new development is introduced. So if we take this along with the Grill et al. Findings and the projections for future development, which have been summarized already by different global dam data sets, then we can presume that as we move into the future, particularly with an emphasis on green technology, that we're only going to see more of this flattening effect. Does that answer your question?
Yeah, we'll wait. If it doesn't, then maybe you'll post it again. So I don't see any more questions. I have just one curiosity. So for the work that Servan is doing for the continental scale routing, so when you're developing this kind of big continental scale of, big continental scale of models, how do you decide what level of local complexities that you want to represent? I mean, there can be so many, regional characteristics, but also local phenomena like reverse flow, split flows, right? But you cannot address everything. So how do you decide, like, okay, this is the level of local complexity we'll address, and because we are doing global scale, so how do you decide on that one?
Yes, that's an excellent question. Thank you. We call it global scale because of the way the code is can handle, like, let's say 3 million river reach globally in a matter of minutes for a year of simulation. But nothing prevents us from going into local scale and see the details. Actually, we can do that. We have the capability to do it, and we can basically make the model as fine as possible for headwater catchment and test different hypotheses at that scale. Regarding the processes that can happen at a smaller scale, that's another story that, yes, probably for each case and each new processes that we have to check, for example, effect of ice, if there is, or other things, but that comes along with I would say with the need and the exploration. Did that answer your question?
Yes, thank you, Servan.
Yeah.
I don't see any more question. I'm just gonna count to 3. So if there is any urgent last question, please send us a up. If not, we'll be moving towards wrapping the webinar. All right. Thank you again, Trisha, and thank you all the panelists. And I also want to thank everyone who attended this seminar. Just a reminder that next month on 7th of January, we'll be having Professor Martin Clark from the University of Saskatchewan, who will be presenting in advances on geospatial intelligence. So please stay tuned. That will be all for today. Thank you, everyone. Trish, you want to say any last comment?
Yeah, just thank you for the venue to be able to present our work. I'm really proud of the work that my team is doing, and thank you to all my team members, and hopefully we'll have a follow-up in a year or so to update you on the progress.
Thanks. Thank you, everyone. I wish you a good day. Bye.